All right. Let's just get this.
You can, like, 182 views for fall 2014.
Yeah, that's only for that initial video, though, right?
No, that's fall 2014, 4431.
Oh, that's for PChem.
Oh, 56 views. You can click on it individually, and it'll tell you how many people look on it.
Huh. All right. Because I know how to look at this. There's this thing called attention statistic that shows when everyone quit watching or they fast forwarded or rewound. That's kind of neat to look at that. You see where I really confuse people or not. Okay, let's get this out of my system because this, I'm just guessing people aren't that comfortable with because they haven't had that much practice on it. So hopefully this is somewhat similar to your notes. It's on EX5. Circle the oxidizing agent, place a box around the reducing agent. So let's just focus on A for now. And I know we talked about reviewing for the final too, but if we don't have time, we can make time later.
Is the final going to be like a copy and paste?
In fact, for the final, to review for the final, we can just do that for lab checkout, right? Bring all your exams for that. That lab, because there's nothing really to do on that day, right? Brandy just takes all of your material, Ricardo, and puts it in her cabinet, and she's done.
All my material.
Your beakers and stuff.
Is the final, sorry, going to be like a question statement?
Yeah, I'm going to copy paste off of the, well, I'm going to change the numbers, but I'm pretty much going to copy paste off the exams.
Off the other exams? Okay. As long as I study Gloriana's exams, I should be okay.
Okay, so what did you circle for A? Oxidizing agents get reduced. So this guy is +2. Let's just look at the easy one. Well, I guess they're both the same. So manganese goes from +2 to what? What's manganese right here? Oxygen is -2. So I've got a total of -8. There's only one manganese. So whatever plus -8 has to give me a -1. So manganese has to be 7. Okay, so this manganese 2 ion got, the only way I can remember this, Andy, manganese 2 got, so when I say manganese 2, I'm talking about this guy. Manganese 2 got oxidized or reduced. And manganese 2 got oxidized, so manganese 2 is the reducing agent. And what am I supposed to do? A box around the reducing agent. So that should be a box. So do I have to, don't do any calculations, just circle that one. I mean, if you want some practice, great, go ahead and find out that bismuth got reduced, but okay. So that's it. Now let's write balanced half reactions. So identify the two. They're not asking you to add them up or anything. They just want 2 balanced half reactions. Well, if you add them up, you get the overall balanced reaction. But oh, it does ask for that in number 3. So write the 2 half reactions, then the overall balanced. It does want all 3. I must have changed that. And it's an acidic solution. So you remember, first you balance the element. Then you balance O's by adding H2O. Balance H's by adding H+. Last thing is balance the charge by adding electrons to the most positive side. Yeah, there it is down here. Oh, now you could get lucky, right? And that half reaction could very well be in that table of standard reduction potentials. So then you could just copy it. But we're going through this as an exercise to make sure you know how to balance these. So if you just copy it, you're defeating the purpose of this review. Because if I give you one on the exam, what's the point of having you copy a half reaction from a table? You're not learning jack, right? You can't exhibit that you've understood much. So I don't think the bismuth half reaction is in there anyway, so you can't copy that one anyway. But the manganese one probably is. So Kimberly, remember how to do this? All right. This would be the starting point for each one. Then you balance O's by adding H2O, H's by adding H+. Balance that charge by adding electrons to the most positive side.
So is that always going to be the case when you try to balance the O's with the H2O?
Always.
Okay.
Because they're always aqueous reactions. They're always in water. If they're not, man, we're screwed. We have no rules. We're up a creek without a paddle.
Creek.
Creek. This is Texas. They're cricks, aren't they?
Yeah.
I think this is the most confusing part. Is that dang charge, right? Did you see where the eight came from, Ida? Because I have 4 times 8 H's, so I have to have 8 H's.
I don't think that.
Okay. So I think the confusing part is the charge. To get the charge, multiply the stoichiometric coefficient times the charge and add them all up for each side. So I'd have 4 times 0 plus 1 times 2. So this is just positive 2 on this side. I have 1 times a negative 1, 8 times a positive 1. I have a total of positive 7. All right. Definitely charge isn't balanced. Desiree, add electrons where? To the most, what side? The most, electrons are negative, so add them to the most positive side. So you gotta add how many to that permanganate side? Here's the permanganate side. This is definitely the most positive side.
Oh, 5.
5 of them. Because then I'll have positive 2 on both sides. Do the same thing to the bismuth half reaction. Get it balanced in acidic solution. O's by adding H2O, H's by adding H+. Electrons are the most positive side. Once you get it, then you add the 2 half reactions. Just make sure you cancel the electrons out. So Sabina, where'd you end up adding electrons? Okay, and how many? Five? Well, let's do this side first. This side is a total of 3 times 1, 3 times 0. This side is 3. The other side is 5. 2 of them. Good. Okay, now you got to get stuff to cancel out. You have 2 balanced half reactions. So you got to multiply through the whole side by 5. Both sides by 5 for the bottom one. Both sides by 2 for the top one. Then we get stuff to cancel. And I would just write your final answer down there. In fact, you might even, so you don't have to rewrite the darn thing. You might as well fix it up. I'm going to have 2 times 8 is 16 hydrogen ions. 5 times 6 is 30. 30 minus 16 is 14, right? So I'm going to write 14 hydrogen ions down here. And just forget those guys. The waters, I've got 15 on the one side, 8 on the other, so that's going to be 7 waters over here. This way I don't have to rewrite the thing. If you don't want to do that, just, cancel them out after they're nice and clean and rewrite the whole thing. But nothing else is going to be canceling out, so you just write everything else in. I'll have 2 manganese 2 ions. 5 of those complex ion bismuth polyatomic ions. I don't know what that's called. I've got 2 permanganates, 5 bismuth 3s, that should be it. And you can, usually I just check the oxygens or something to make sure it's balanced. And I've got 15 oxygens on both sides, so odds are it's good. Since the oxygens show up in a lot of places, if they're balanced, odds are it's good. Okay. Now, if it would have asked for E0 for the reaction, well, then you just have to look up, you need a table, you need an E0 for each of these. And then you'd have it. But it didn't ask for that. So. Did I screw up here somewhere? 5, okay. So I have 2, see that's where I shouldn't do stuff in my head. I almost always screw up. I have 2 times 8 is 16, 16 H's. 5 times 6 is 30. So 30 minus 16 is 14. So I canceled out. So you could write up here 16 hydrogen ions. And 5 times, I have 30 hydrogen ions. So that's what I'm canceling out. 30 minus 16 is 14. So then I wouldn't have to rewrite the whole thing. So you can do a lot of scribbling up here, just like this, right? And it's showing your work.
The same with the water. It's 8.
Yeah, same with the water. I should have wrote an 8 here to make it cleaner, and a 15. So then 15 cancels out with the 8, just leaving 7. Yeah, I should have wrote that. That'd look better. It doesn't take that long. Let's just try one more of these. Just try B and then call it quits. If you can do B, you're good. So remember the first step was they wanted you to draw, what was it? Circle the oxidizing agent, place a box around the reducing agent. So do that first. And notice how, if you look at this, I would mess with the sulfur. Because if you mess with the nitrogen, because your choices are either sulfur or nitrogen, right? Those two elements, they're the only ones that are going to be changing their oxidation state. So if you pick the nitrogen and work with that compound, you have to calculate it on both sides. But the sulfur, you don't, because S8, you know S is what? In those rules, you have an element in their most natural state, it's 0. Maybe you didn't know sulfur is call it orthorhombic or something, but that's how sulfur exists in nature, S8. But an element all by itself, remember the oxidation state has to add up to be the charge anyway, so you could follow that rule. If you didn't know S8, you'd say, oh, well, this doesn't have any charge to it, so I have to add up 0 8 times. It's the only way to get it. So sulfur has to be 0 here, so just figure out what it is over here. And then you'll be able to identify what sulfur got oxidized or reduced. So Marlena, did you circle H2S or did you put a box around it? So it ends up being 0, right? Oh, I don't know. What is sulfur's oxidation state in hydrogen sulfide? Its oxidation state is what number? Because H has to be what? H has to be 1, right? Because why? Well, don't forget everything that you know about acids, right? You get a lot of H plus from acids, so and that's the rule too. Hydrogen is +1. There's exceptions, but we're not going to mess with those. So remember what you did before. Like S is, if you know S. You're looking at this is sulfide, S with -2. And that's kind of your answer there. You can think of it that way. This has to be -2 because you recognize that as sulfide, right? Or see, you have 2 times a +1. Whoop, so this is really a +2. This has to be a -2. Or just recognize it as sulfide, either way. So anyway, hydrogen sulfide, circle it or box? Circle is for oxidizing agent, box is for reducing agent. Circle, because it got, hydrogen sulfide got reduced, so it is the oxidizing agent, so circle it.
Would it work the other way if you decided to use
The nitrate?
Yeah.
Oh yeah, oh yeah. I'm just saying, since exams are timed, and you get the same answer, there's an easy way and a hard way. But yeah, oh yeah, you get the exact same answer. You have to. All right, so then to get the 2 half reactions, balance it, get an overall reaction.
The nitrogen went from
Oh, you want to do the nitrogen one?
yeah.
So this is a -2. I've got a -6 total. So that means nitrogen here has to be a +5.
Okay. And then he goes to being a +4.
Then he goes to being a +4.
So he's gaining an electron, right?
You got reduced. Oh, something's messed up.
So he's oxidizing, right?
They both got reduced. Yeah, something's messed up. This NO2 has to be on this side. I'm glad you noticed
Did the
this.
sulfide get oxidized? Because it went from a -2 to a 0?
Yeah, that's what I was
Oh, that got
thinking.
oxidized. So it's the reducing agent. What did we say? Did we say the other one?
Yeah, we switched it around. But that makes sense because sulfur goes from -2 to 0, so
He got more positive.
so he's a reducer.
More positive. What did we say? We didn't say the right answer? More positive. So that means he got oxidized. So that means he is the reducing agent. That's supposed to be box. Did we screw it up? Reducing agent gets box. We did screw it up. No one spoke up. I didn't notice that. Okay. So 5 to 4, that gets reduced. That's oxidizing agent. That gets circled. How did we miss that? Yeah, going from negative to 0, negative number to 0 is getting more positive. That's getting oxidized. Yeah, first I thought I wrote the reaction wrong. So there's the sulfur half reaction balanced. I ended up with 16 electrons on the sulfur S8 side.
Then I also had one more question. How'd you know to put water on the right side, not the left side? I was having trouble with that.
Where, on the bottom one?
Yeah, on the bottom.
Because you have to balance the O's by adding H2O. Here I have 3 O's. Here I only have 2.
Oh, I see.
So I need to have an O. Otherwise my O's aren't balanced.
I see. I was just thinking, like, you know, you mess around with, like, the stoichiometry or whatever, like the numbers in front of that NO3 and NO2, but I don't know. If
I ain't
that
gonna.
would never fix it.
That would never fix it.
Right?
So 2 H's, 2 H's. I'm gonna have a +1 over here. 0 over there. So it's only 1 electron then. Get the same charge on both sides. Man, multiplying the bottom one through by 16.
Why is the left side +1?
Because I've got the coefficient times the charge. So 2, positive 2, and 1 times a negative 1. And the other side is just 1 times 0 plus 1 times 0. Let's see, so I can fix 32. He's gone, he's gone. Yeah, 48 oxygens on both sides. Okay. So those are about as hard as they get, but if you can do those, you'll be set. So again, if they wanted E0 cell, these guys would have to be in the table. So then you could look them up. But they're not, I don't think. Okay. So I don't know how far you got on this review if you started, but a lot of this we kind of covered already, right? By just working those balancing half reactions, right? We've talked about this kind of stuff. We've talked about this kind of stuff. Okay. Did you want to start at the beginning, or did someone have somewhere they wanted to jump to?
Yeah, I like example 4A.
Example 4A. Okay. In a beaker is dumped all this stuff. What reaction is most likely to occur? Now, do all these numbers matter? No. You just care what's there. You don't care what all these concentrations are, right? And all these amounts of things. I mean, they didn't even tell you volumes. They could have to make things even more confusing, but it doesn't matter. The pH doesn't even matter. But it's nice because then the idea is when they tell you pH and it's pretty acidic, now there's an appreciable amount of hydrogen ions. So when you pull out that table of standard reduction potentials that should be next to you, and you're trying to find half reactions that are possible, if there's H plus in there, it doesn't rule it out because there's some appreciable amount of H plus. So my game plan for this is to identify some half reactions. Okay, and I pick the two that, where one electrons are on each side, and pick the two that are the most positive. And then those are the two whatever combination gives me the most positive answer, right? Those are the two half reactions that I'm going to pick. Okay? And I don't care how many electrons are each side. I just have to have something that's being reduced and something that's being oxidized, or something that's reacting with electrons and something that's producing electrons to complete the reaction. So that's the game plan, and I use the table of reduction potentials to do that. So let's start, and we can just list them all out. You can list them all out as reductions, and then we can see in our head once they're all in the same spot. Just copy them all from the table. I've got Fe plus 2 plus 2 electrons going to Fe solid. And that is negative 0.44 volts. And I'll write the other half reactions. But I wrote this one down because odds are I'm not going to pick it written this way, but I could very well pick it reversed if I don't find anything that's more positive than 0.44 volts. That's a reversed reaction. Okay? So identify each of those half reactions and just kind of write them out. And I would just list them out all as what's in the table. Don't do any flipping or anything. Just write them all as reductions. It'll probably be easier to pick out. It's a cleaner starting point. So we've got the iron ones done. And then here's find one with these two. Find one with these two. And just list out those reactions and write out their E zeros. Just copy them right from the table. If they're not in the table, you can't do this problem. So they got to be in there. You just got to keep looking. Man, there it is. Couldn't find it. Okay. So let's clean this up. I just erase all of it. Okay, so which two are you going to pick? Let's number them 1, 2, 3. So what are you going to do to 1 and 3? Flip 1. Is there a combination? Here, Brandy said she's picking 1 and 3, and she's going to flip number 1. Does anyone see a combination that's going to give you a more positive answer than that? 2 and 3, but one of them has to be flipped.
Yeah, no.
Yeah, I think she's got it, right? So make sure you can see that. 1 and 3, but you got to flip number 1. Now that doesn't mean the other reactions aren't going to happen. Just remember, you can calculate equilibrium constants for all these overall reactions, and they're not near as spontaneous. There's a degree of spontaneity. Those equilibrium constants are going to be very small. You get a very small amount of product. But this one, you can get a huge amount of product because the E0 is so positive. So 1 and 3, but flip number 1. So they want an overall reaction, so you're going to have to cancel those electrons out. Okay, so there's our answer for A. And, oh, Kelly, what expression do you use to find B? Oh, you could use that for, that's exactly right. If we had a table of delta G's for everything, we could add up the delta G's for the products minus the delta G for all the reactants. But I'm not going to give that to you. And you can't use your cell phone. So you can't do it that way. Jackie, what expression do you have to use? Yeah, and I give it to you, but she knows what she's looking for. Negative N, F, E. Okay, so here, this is the equations given to you. But it's delta G 0, so that means what conditions? Standard. So if I put a 0 here, where else do I have to put a 0? E cell. Which is thank goodness, because that's what we have. We have E0 cell. Okay. So what are you going to put in for N? 2. F? 96,485 coulombs. And I gave you that number. That's the charge in 1 mole of electrons, 96,485 coulombs. Right? So you just said you have 2 moles of electrons. They give you the charge per mole of electrons. And then you plug in E0 cell, which is in volts. A coulomb times a volt is, what unit answer? Joules. Negative whatever. Does anybody get a number so I can put that in? I'm too lazy.
Negative 395.6 kilojoules.
Oh, kilojoules. Okay. Or 3.95 times 10 to the 5th, right? Negative. So somewhere around there, you're doing good. Find the equilibrium constant. Okay. Oh, Ida, now we need an expression to get big K. What expression are you going to use? And this I really don't give to you. Right? And all these handouts and whatever you get for the exam. Do you remember? Start with whose equation? Nernst. Okay. And that I do give to you. It looks like E cell, what's it? E0 cell minus 0.0591 over n log of, do you want to remember? Log of? Q. Okay. You're at equilibrium. So now you change the Q to a K. Now you got to change something else though. Otherwise you're not at equilibrium. That voltmeter has to read 0. There's your, so if you bring the E0 cell over to the other side, it's going to be negative. Those negatives will cancel. You pretty much end up with E0 cell equals 0.0591 over n log of K. And this number is going to be huge. And because it should be huge. This is a spontaneous reaction. I mean, look how, this is a very, very spontaneous reaction. A huge positive potential. This really wants to happen. That means you're going to have a heck of a lot of product. This could be 10 to the 80th or something. Some crazy high, huge equilibrium constant. Wow.
Dr. Smith, what would be the wording for using Q as opposed, like I know equilibrium constant is K, but what would the wording be for Q?
What the heck happened? Let me get this back and then remember your question. Weird. Okay, so your question was what?
What would the wording be for Q?
If you're going to not use K and use Q.
Yeah.
I think that's when they want to measure the potential of the cell. Because if you're at equilibrium, if it says you're at equilibrium, they can make it as complicated as they want. What's the potential of the cell? You don't even need to read the question. You write 0. But if they say, what's the potential of the cell? What does the voltmeter read? They're not going to say that. They're going to say, what's the potential of the cell? Right? And then they give you all these concentrations. Well, then you got to plug it into the Q expression. And you also use the Q expression when it's a little chemical sensor. You want to solve for one of those concentrations in the Q expression. Those are the 2 times that you use Q. So anybody get a crazy, huge number for this? Times 10 to the 69th. It should be, like I was saying, it should be really, really big. Anybody else get that? Something close to that. Jeffrey, did you get something close to that?
I got 2.01 times 10.
Okay. Well, let's just stick it to the 10 to the 69th part. Should get really close to 10 to the 69th. Here, this is this is a good one. This answers. Leads right in. D answers leads right into what Monica was asking. When do you use this Q? Well, here's a good one. Calculate E. They're kind of missing a little subscript there. E cell. And delta G for the conditions described. Will the reaction occur?
Dr. Smith, going back to part C, is it supposed to be negative 0.0591?
When I bring E0 cell over to the other side, it's going to be negative. Negative signs will cancel.
So you can just put a 0 where E cell
You have to.
Okay.
Not much choice.
Oh, because it's at equilibrium.
Because of that equilibrium.
Okay, that makes a lot of sense.
It's done.
Okay.
Your battery is dead.
I'll be there when we reach it.
So when you do D, what's the game plan for D? Use whose equation? Use what equation? Yeah, use the one we wrote up here. Just plug everything in and solve for E cell. And then they want delta G. Great. Same expression as in B. Just get rid of the superscript zeros because you're not at standard conditions.
So you just plug in the K that we got into
The
E
K.
cell equals E cell naught. Is that what that's called?
The K.
Minus.
You're not at equilibrium.
Yeah, I guess.
It says for the conditions described. They're referring to which part?
Oh, the concentrations.
Yeah, way up to part
I
A.
got you. Okay.
To make this question really good, I should have given you volumes. Because then you would have had to have calculated the concentration of everything up there.
Please no.
Right?
It's like this one problem just be our test.
And then make it activities.
Oh my god.
This could be a cell that's monitoring something in someone's blood and their life depends on it. It could be a really big deal.
Or not.
Where is C? Oh, cesium plus 4 is 0.29. Do you see where I'm getting that stuff? It's going to be the concentration, just looking at the overall reaction. That's where I'm getting this from. The concentration of iron 2 times cesium 3 squared divided by concentration of cesium 4 squared. And I get an E cell.
Did anybody get 2.04?
2.04?
Yeah.
Nobody else get 2.04? Around 2 volts?
Let's see who.
Okay. So it's right around 2 volts is what you should be getting, and that's positive. Is what it sounds like.
Yeah, probably.
What'd you get?
Around,
2.04, and she got 2.06.
I got 2.
okay, so around 2 volts. So will the, so we just got E cell. find delta G.
That's because there's no 6 up there on the 0.05 magma, so that's what's knocking it down. Or less.
So will the reaction occur? Most definitely, right? It's a huge negative delta G, or it's a huge positive E cell. Extremely spontaneous, very high degree of spontaneity. Huge equilibrium constant. Kind of all ways of saying the same thing. So we've got some stuff at the beginning. We've got more stuff in the middle. Number what, 7? Okay. Check out number 7. Okay. For, in my mind, when I'm messing with these types of problems, they want to know how many grams of indium solid are involved. So I treat them like one of those big, long dimensional analysis problems, because that's how we've been handling. That's been our weapon for a lot of different things, especially when you're converting one unit to another unit. So you start out with that. And where electrochemistry, I think, is really gets you is, first that we got to see this. Here's a mole bridge. It just involves non-traditional things, like 3 moles of electrons for every 1 mole of indium. So if we could use this mole bridge of electrons to indium, we're set. Because then you just use molar mass of indium and you're done. So this is where Faraday's constant is. You just got to remember it. There's how many coulombs and 1 mole of electrons? What was the number? 9645. And 1 mole of electrons, there's 96,485 coulombs. Now we're done. You do mole bridge from the reaction, from that half reaction. Use molar mass of indium. You're done. You have it converted from you converted from coulombs all the way to grams. Indium, what the heck? I don't think I've ever used indium in a problem. 114.8. Right? Do you ever recall indium good for anything?
No. What was it again? Like 114 point.
1.8?
Yeah.
Okay.
Like 7 or 1.8.
Right around 1.8. How do you do B? Since this is a review, let's just review a couple things. What really helps me in this stuff is to know the units. Current has what unit? Big A. Big A for what? Amps. And an amp is a what over a what? Coulombs over seconds. Really helps me because then if a problem ever involves amps, I realize, oh yeah, well that's so many coulombs per second. So if they give me seconds, I can multiply it and get coulombs, right? Or in this type of problem, I want to know what amps are, so just divide the coulombs by the seconds and I'm done, right? Another one would be volts. A volt is a electrical potential energy per unit charge. Or what, Jeffrey? Joule per coulomb. It's not as useful as this one. This one is, I think, is more useful. But so just convert the hours to seconds, and then divide coulombs by seconds, and you got it. Pretty sure an hour is 3,600 seconds, but
Yes.
then you'll get it.
What is it over N?
What do you think that is? Try to look at the question, see if you can read what it is. It's 1.5 what?
What?
0.83 amps. Thank you. There's 7B, 8. Any other ones? Monica? Goldfish problem?
E6.
What's that, Monica?
E6.
E6. Yeah. Okay. Okay.
Just use logic to answer this question. Probably not.
Yeah. From Walmart, odds are they will swim in circles.
Walmart.
Hey, you're
I
back!
am. I made it. I survived. I survived the cold.
Probably not.
Did you spend some time at Smithsonian?
I did.
Oh,
Natural
if you
history,
didn't, I would have hit you in the back of the head.
Air and space, American history is good.
Awesome. Okay, write the Nernst equation for the electrochemical reaction occurring within your probe. Well, if you're going to write a Nernst equation, do you need the overall reaction? Yeah. In fact, you need a value for E0 cell. So you got to identify the two half reactions, find their E0s, get the overall reaction. There's a lot of preparation in getting that Nernst equation. So try it.
Where's the CRNX plus on this table? Is it in here? You might have to look in the book.
CR solid and CR2 plus.
No. I mean, it would just be the same thing as a plus
Let's do it from home.
I don't see one in here.
I'll look in my book.
We need another table. Well, you know, we can just change it to 3. Who cares, right? Wouldn't that be a lot easier?
Yeah.
Let's just change it to 3. And trying to Google it and all that stuff. So everything is changed to 3. Remember the cathode there that involves platinum and hydrogen? That platinum is just a catalyst. That's that standard hydrogen electrode. So you don't write that in the reaction. It's just H2 going to H+. The anode, where it's producing the electrons, that's chromium-3 going to chromium solid. Right? Is that even written right? I don't think it's even written right. Yeah, I wrote the cell reaction wrong too. That's all right. It'll still work.
So would you need to flip the hydrogen up there?
Oh, that's a great question.
For the electrons to cancel out?
Let me- okay,
Yeah, you have to
when you,
negative one.
let's see, hydrogen.
Because that these two gas is 0.
Yeah, that's our standard hydrogen level. That should be 0. Okay. When you're given the cell notation, that is the inner workings of how your cell is built. So your cell is built this way. So you have to You can't do any flipping. You have to have this as a reactant, that as a product. That's the convention of cell notation. You always have reactants going to products, and you have that little line if they change state, or a comma if it's the same state. So, and then you have double lines for salt bridge. And here they have a catalyst, and since this is a different state, they have another line there. So, no, there's no flipping at all. This is not going to be a galvanic cell. This little sensor that was built has to be plugged into the wall. Or it has to be some battery supply. It has to force this reaction to happen.
Is the chromium and the chromium solid on the left side of that double line, is that the anode?
So you noticed it. I think, this for galvanic cells, yes, you'd always have the most positive over here because that's the anode, and that's we're so used to doing that. See, I just make up these questions really quick, and I didn't realize it. But this is more real life what I did, because you're right. I have to force this to happen. It doesn't want to happen. So I see what you're saying, though. It's not following the convention. My notation up here, I don't have a oxidation reaction happening here. So my cell notation, I screwed up when I did it, actually. Because you have to have this has to be the anode. Anode by definition is oxidation. Producing electrons or reacting with electrons? Anodes. They produce electrons. So, and that's how you're supposed to write it, whether it's going to be spontaneous or not. Okay? So I screwed up writing that cell notation, so don't even worry about it. But let's just pretend the cell notation is right and just realize, for the purposes of the activity, it works. But I screwed up writing this. I should have had, because this is not an oxidation reaction. Then I'd be changing everything. So I just want to stick to what I have here. Okay?
So the stuff on the left side of the double line should be producing electrons for you?
Because,
right?
Yeah, whenever you have,
Okay, that's what I was thinking.
whenever you have this has to be the anode, and this has to be, and whether it's going to be spontaneous or not, it doesn't matter. This is their convention. So when I made up this problem, I wasn't paying attention. I wasn't producing electrons on this side. Don't worry about it. It still works.
Oh,
Right?
I just thought that meant that we would like switch the guy around. And
No,
or he's
we're going to follow that rule with cell notation. With cell notation, you have to have reactants going to product. You have to otherwise you're not following the cell notation. I'm not following cell notation because I forgot to write anode, produce oxidation as an anode, reduction as a cathode.
So you're saying that cell notation is telling us that Cr3 plus turns into...
All I need to do to fix this is put this description, I can't jump that high, put the standard hydrogen electrode where? Over here. Copy and paste my chromium +3 line chromium solid and paste it over there. I just screwed up writing the cell notation. That's all. See what I mean? It doesn't change the problem at all. It's just improper notation. Because anode technically is supposed to be on the left-hand side. I wrote my anode anode is supposed to be on the left-hand side. I wrote my anode on the right-hand side. I just kind of screwed up. But it doesn't change the problem. It doesn't change the sensor. In fact, maybe it hides it more because now people try to build my little sensor here and they're going to screw up. I don't know. Don't worry about it. Okay? But it's a good catch. If you see that, you're reading cell notation correctly. Okay. So cell notation, you can't mess with it. You have to write what they say as a reactant as reactants in your half reaction. You have to write what's a product is what the cell notation says is a product, right? The cell notation says that this is a product. It says that this is a product. So you have to write those as products in your half reactions. It says it. You have no choice. It says that these are reactants. So So you have to write them as reactants. I just wrote them on the wrong side of my salt bridge. It doesn't really change anything, though. You still end up with a negative 0.74 volts for E0 cell. So we still haven't written the Nernst equation, but we're pretty darn close. Okay, so how'd you write your Nernst equation? What'd you write first? Negative 0.74 volts minus
0.0592 divided by 6.
over 6. All right, and don't write log of Q. That's not going to help. It'll be what over what? To the third? Or to the... Oh, to the 6. To the 6, yeah. Okay, good. And keep going. Then on the bottom, I'm going to have chromium 3 to the second. And, oh, we don't use brackets. We're supposed to write what? P of little h2 to what power? To the third. That is my Nernst equation. Because that's, you're supposed to be using the, going way back when we had expressions with Gibbs energy and calculating equilibrium constants, you're supposed to use big K and not big K with little c. If it was little c, everything's in terms of concentrations. So it's not. This is the equilibrium constant expression we're supposed to be using. Technically, they call that the thermodynamic equilibrium constant. So that means, yeah, concentrations for everything, great. Leave out solids and liquids, great. Except gases got to be in their partial pressure in units of bars. So that's why we do it. Otherwise, you're not going to match all the tables. You're not going to get those delta G values to work out. So, would you buy those goldfish? Will they all right? So the problem really wants you to do what? Solve for the concentration of what? Of H plus. Here's the qualifier. You're going to swim in circles if your concentration of that chromium is supposed to be 3. is bigger than 0.25 molar. So use your Nernst equation as a little sensor and solve for the concentration of chromium. And if your answer is bigger than 0.25 molar, don't buy the goldfish. If it's less than 0.25 molar, you're fine.
How would you set that up? Like, what would you use for the concentration of
It's got to be in the description. Here it is. There must be some buffer or something. It's staying at 5.4. Or at least at that instant in time, it's 5.4. Oh, interesting. Hydrogen isn't 1 bar, right? So be careful with that. At least it's in bars, though, so you don't have to do any converting.
rings to the 6?
On that calculator,
Yeah.
just push x to the. Put in your number first, and then put in x. Where is it? X to the y. You see x to the y? It's right above the c, and then push x to the y. Then push 6.
When you say 10 raised to all the junk to the left, it turns into a 0, and then when you try and divide the h plus to the 6 divided by that, it gives you probably nothing, right? Do you have that problem?
Yeah, just a 0 like that.
Because if you try and divide any number by 0, you're going to get something bad.
I don't know how you're getting 0. Let's see.
10 and negative
Yeah, mine does
5.4.
too.
0.485 volts. Maybe I messed up.
So that's CO3 plus 8 minus and stuff.
Hydrogen ion, 5.4. Okay. So you guys are having trouble. It's 0.485.
Yeah. I just got up to it.
Negative 0.43. Let's write some intermediate steps here. Whoop. equals that mess. Not log. Log's gone. Yeah, I mean, I'm going to run through it one more time here. Whoa, how'd I get negative 0.43? Man, I got negative 74 now. What the heck? Negative 120. Do you get negative 124 here?
Yes.
That's where I messed up. So this is all messed up. So I probably have voltages and that are going to give ridiculous answers.
Because whenever you raise
Yeah, it's getting to a 10 to the negative 1. It's ridinky dink, right? So I screwed up with putting in numbers here. I'm in making the question. So, but the point of the activity is you see what to do. You're supposed to solve for this guy, right? So we've got a lot of homework problems and in-class problems that have numbers that make sense. So don't put too much stress on this. Just realize the game plan. And the game plan is you use the cell description, you use this to get that, right? Which is huge, so then you can write this. And then there's something in here you had to solve for. It always works out that way. But the point is you're going to start with the cell notation, out of the cell notation, get the half reactions, right? Look up their E zeros and things, so you can write the Nernst. Because inside that Q is going to be the little sensor, whether they're looking for copper or iron 2 or whatever the little sensor is looking for. That's what you're going to solve for. Okay, it always works that way. So this problem is good up to this point, and then the numbers are messed up.
Very algebraic problem.
Okay.
It was very algebraic problem.
Life isn't perfect. All right.
So I still don't know if I should buy the fish.
Oh, you should definitely buy the fish because look at there's no way. I mean, it's an extremely small chromium concentration. Because the problem here is that, well, I gotta mess with the numbers and make it make sense. Okay. So, but you've got a lot of other problems that numerically made sense. So it's the game plan that we're after in a review. And if you can see the game plan, you'll have a game plan for the exam. There might even be another one. There's another one. Oh, they're using the chromium-3 probe again.
The 7B looks kind of cool.
We just did it.
You do that one?
No.
But I think we wrote the
Where's the really hard one?
but what's nice about 7B is that we did a chunk of it already, right? To find the overall, those half reactions and things, nitrate and H2S. Here it is. Where did it go? Here it is.
The molecular weight of F8 is 256.52.
All right, but the point is what you need is there, because you start out with a 24.8 of S8. Is that confusing? The 24.8 grams of S8. And you want to convert all the way to what? What do you want to convert to? The final answer is amps. Right. But you're not going to get there right away. Because amp is what over what? Coulombs over seconds. The question gave you which one, really. It gave you the seconds. You just got to do a little bit of converting. It gave you that part. You got to get the coulombs. So convert the 24.8 grams of S8 into, yeah, but in the final end, convert it to coulombs. That's the trick to this. And then whatever you get, that's what you put in right there for that C. And to do that, you need a mole bridge between moles of electrons, moles of S8 and moles of electrons. And then use Faraday to go from moles of electrons to coulombs. And that's why I copied and pasted this whole thing, because here's your half reaction that you're going to need right here. It has moles of S8 to moles of electrons. You need that. And then you got it. You need that mole bridge. The overall reaction doesn't do you any good because it has moles of S8, but there's no moles of electrons in there. So you can't get coulombs out of that. So you had to use the half reaction. Yeah, so I would do molar mass first, and then the mole bridge. Mole of S8 for 16 moles of electrons. Then Faraday's constant. Right. Mole of electrons is 96,485 coulombs, and you'll have it. You got 2.9?
82.9.
82.9. I don't hear any other takers.
I got 82.9.
Okay. 83 amps about, it sounds like. EX8 is very similar, I think, to 7B. Like that chromium on.
On the next page, it's 1.2.
This one? EX8?
Yeah.
Okay. Do you see a game plan for this one? This one isn't a sensor thing, so we're okay. Our numbers didn't really matter. All you need is you need the mole bridge to solve this one. Hydrogen's explosive, so if you get more than 10 grams over 2 hours, you got some issues. You gotta put a special sticker on there. If the current draw on your probe is 1.2 milliamps, okay, so you see what you gotta convert from what to what? You see the big picture? You gotta convert from what to what? Now don't start with this. This is your that's what you're supposed to compare to, because it says, does your probe require special modifications? So you have to calculate something and compare it to that. So that's not the starting point. Yeah. Now, you're going to get what out of that? And really convert what to what? Get coulombs out of this. Get coulombs, and then convert it to good. Get coulombs, then convert it to grams of, what are they interested in? Hydrogen. Are they talking about H plus or H2? H2. H2 is the explosive stuff. So from the 1.2 milliamps, get coulombs. And then out of those coulombs, get grams of hydrogen. So you're going to need a mole bridge to do that. You got to remember, when you start out in the very beginning, you got to remember what milli is. Remember what an amp is, so you can solve for coulombs. Milli is 10 to the negative 3. And instead of writing amp, I could write what over what? Coulombs over seconds. So just multiply that by the number of seconds. What's the number of seconds I have to use? 2 hours. 2 hours worth of seconds. I think there's 3,600 seconds in an hour, so that would be like 7,200. 72,000, really? I thought there's 36.
Yeah, sorry, it's my bad.
Yeah. It's getting dangerous doing stuff in my head. I hardly ever get that right. Okay. So there's our coulombs. You're going to need a mole bridge. And we can copy and paste that. Where was that? That swimming in circle thing. Here it is. You need your half reaction. Lost my arrow. There's 2 moles of electrons for every 1 mole of H2. So start with those coulombs. Go from coulombs, moles of electrons, moles of electrons, moles of hydrogen, moles of hydrogen, grams of hydrogen, and see if your answer is bigger than 10. Oh, there's looking at Marlena's, there's this E0 prime thing. We didn't talk about that in class. She's on page 125. We're not messing with E0 prime. Biochemistry is supposed to. I don't know if you guys do that in biochemistry.
Is it? It's in a 1-to-1 nose of 2? Oh.
And that 2 moles.
It's so weird. I got something that was like way less than 10 grams of hydrogen, but I don't know.
That's good. Then you have to worry about your probe.
What did you get?
9.02 times 10 to the negative 5. That's what I got.
I got 8.95.
10 to the negative 5 though. So seems like you get around 10 to the negative 5 grams.
10 grams is a lot of hydrogen. 2.016.
So you're fine.
I think it's 2.
Hydrogen's light stuff.
Yeah. It really doesn't matter in the end because it's so far away.
10 grams is a lot. I got to change that question. You're going to be way over the explosive limit there. That's a lot of hydrogen.
I'll do the test. I'll look over my question like 3 more times.
But you got to show your work anyway, though.
So for the test, we're not doing number 9?
That E0 prime thing? Yeah, exactly. That's on page 125 in your outline there. Yeah, we're not. E0 prime is all they do is in biochemistry, the pH is such a big deal and they leave it constant all the time. All they do is they pull the hydrogen ion term out and they combine it with the other constants and make one big term. So it's supposed to make the calculations easier. But so it didn't seem all that applicable.
So the E0 prime thing we can just forget.
Yeah, we didn't even talk about it in class.
Yeah, if we wanted to do biochemistry, we'd be in that other one right now.
Mm-hmm.
I got like 8 something.
Times 10 to what power? Well, what do you have here?
8.64.
All right. Then what number did you put down here? What number did you put here? What number did you put there? All right. You got to put in the numbers. I didn't do all that for you.
They're going to be size question.
So just practice these. The more you practice them, the better you'll get, just like any exercise or activity. Just rounding. That's why I wrote down 10 to the negative 5. Not everyone's going to get the exact same numerical answer. We should, but I don't know why you don't.